bored and just super eager to get started again? Yeah. All right, so I've graded everybody's tests. You can get your PDF, you can see a PDF of your graded test if you log on to Canvas. You'll also see a problem that you've been assigned that you can complete to get some points back on the test. And here's how it works. I assigned a problem to each student. Not everybody got the same problem, but it sort of corresponds to a problem, like similar to a problem that you got points, that you lost some points on the test. So, and then the problem, you know, on the top of it, it'll say earn back points for problem number whatever, like problem number 3 or something. So, like, you can work on this problem, you can get help, you can consult your notes, like that's fine. You're going to turn it in no later than a week from today, and then whatever score you get on that problem, we'll replace the score on the corresponding problem. So, like, if you got a 1 on problem 3 and you turn in your solution and you get like a 4, then I just kind of replace that score on your grade sheet with the 4, with the new grade, with the exception that you can't do worse. So you're not going to lose points. This is a risk-free opportunity. And I hope that you all will, opt in to this. I have the problem sets graded, but I just haven't uploaded them because I'm missing one. There's one that wasn't turned in. So I'll need that soon. I'm going to upload the graded problem sets. I want to upload them pretty soon so everybody can see how they did. And then our plan for today is to keep plugging away through this chapter. We're going to look at the derivative and how the derivative is an instantaneous rate of change, not only of like an instantaneous slope, but we can contextualize it in other ways, look at it in other settings and see what the derivative tells us about certain problems. And then we'll look at other ways to find the derivative that don't all involve setting up a limit as h approaches 0, which will be pretty nice. Are there questions before we get started?
Oh, Rachel, we have a half day on Friday.
Okay.
Just to let you know. So I'm sure we're going to do a quiz, but just keep that in mind.
Yeah, I can make it shorter.
So.
Okay, so let's get started. So we know that the derivative can give us the slope of a tangent line, and that's like an instantaneous rate of change of y with respect to x. It's not an average slope, right? That would be the slope of a secant line, but the instantaneous slope, the slope at a single point, is an instantaneous rate of change. But we can find a derivative and find an instantaneous rate of change if we have a function that exists in other contexts. So one example is, anything that is a rate of change is a derivative. And in fact, say this to yourself 3 times before going to bed every night. Say this to yourself 3 times when you get up every morning. The derivative is a rate of change. A derivative is a rate of change. If you're given information about a rate of change, that means you know information about a derivative. If you're asked to find a rate of change, that means that they're asking you to find a derivative and maybe evaluate it at a certain point. So one example that occurs over and over again is that suppose we have some function that gives displacement over time. Usually in mathematics we say s is the displacement function, and s of t will tell you displacement as a function of time. So if we find ds dt, right, that's the rate of change of displacement over time. Well, the rate of change of displacement over time is velocity. So that's how these two functions are related. If you know a displacement function, you can get the velocity function by taking the derivative. So let's do an example here. they tell us the displacement in feet of a free falling object is given by this function s equals 16t squared. So that's our s of t function. Where time is measured in seconds. We're going to find the instantaneous velocity for the object at t equals 4. So what we want here is we want to find ds dt. That's instantaneous velocity. And then evaluate it when t is equal to 4. So if we think way back to before break, kind of dig deep, we remember that the derivative, when we find the derivative, it involves us finding the expression s of t plus h. So we have to replace t with t plus h. This one's not too bad, it's just a polynomial with a single term. We're going to expand out that t plus h squared. And then distribute the 16. So there's s of t plus h. From here we're going to subtract the original function s of t, which means we're just going to subtract 16t squared. And so s of t plus h minus s of t is equal to 32th plus 16h squared. You recall that, when we're finding the derivative in this way, we set up the limit. I'm going to leave a little bit of space here in between, and then I'm going to set up this limit. So our velocity function is ds dt. This is the limit as h approaches 0, s of t plus h minus s of t all over h. So, the problem that we try to fix immediately, right, that we can think of as our intermediate goal always is we need to find a way to get rid of that h that's in the bottom, right? That's the problem with this limit, is I can't let h be 0 yet because it would make me divide by 0. So I'm going to go back up here where we were working with this other expression and just realize that both those terms have an h in it, so I'm going to factor it out. And so when we come back down here to the limit, I'm carrying the lim through all my steps. I'm replacing that numerator with the expression we just found. So now these h's will cancel. Now it's no longer a problem to let h approach 0. We have one term with an h in it, so as h goes to 0, this term will go to 0, and we just get 32t. So this as a function, 32t, gives us the velocity. That is ds dt. That's the velocity as a function of time. Are there questions so far? Okay. They wanted us to find the instantaneous velocity at t equals 4 seconds, so we're just going to plug in 4. $128. Now, when we're doing problems in context, we need to remember that there should be units attached to our answers. And this one might be a little bit intuitive just because it's a velocity and we know the types of units that have velocity. And if we go up here, we could see that they used feet and seconds. So it seems pretty maybe simple that the units are just feet per second. But I want to just talk a little bit about the notation that we use for derivatives and why I like the dy dx or ds dt notation so much. When you're doing a problem like this, that has a context, kind of an application, the ds dt notation helps us remember what our units should be. Literally, you just take, what are the units of s in this problem? That's feet. What are the units of t in this problem? That's seconds. So the ds dt or dy dx notation helps you remember what your units ought to be for these problems. Questions on that example? Bless you.
Thank you.
Okay, let's try another. Here we have a spherical balloon being inflated, so imagine that the balloon is a perfect sphere. We were going to find the expression for the instantaneous rate of change of volume with respect to the radius. So I'm going to just ignore everything for a second and then just think about what they're asking us to find. It's rate of change of volume. So that's dv with respect to the radius. And so on the bottom is dr. And essentially, I guess what we're looking for is, as the radius changes, for like a little increase in the radius of the sphere, how much change in volume does that create? As the volume gets bigger, I can imagine, as the balloon gets bigger, a small change in the radius can cause like a big change in the volume, just because there's so much more volume to take up when you increase the radius more. We're going to evaluate this when the radius is 2 meters. That's a huge balloon. So we want dv/dr, and that means the first thing we need is a function, an equation that relates v and r. I want one with only v and r, right? I don't want other variables in there. And this is a pretty common formula, but if you forget these, I'm sure they're maybe in the inside cover of the text or about 1 million different places online. If you just look up volume of a sphere, we get the function 4/3 pi r cubed. And I'm just going to use some function notation. So there's our volume. Maybe I'll think of this as my f of r function. So we're going to find the derivative. We're going to find the derivative of v with respect to time, with respect to the radius, which means we need f of r plus h. You might recall that we did some stuff with Pascal's triangle before the break, so that kind of helps us more easily figure out what r plus h cubed is. We have 4/3 pi, and then when you cube that out, it'll be r cubed plus 3r squared h plus 3r h squared plus h cubed. And I'm not going to distribute that 4/3 pi right now. You could, and if you want to do that, that's fine, but I'm going to take a slightly different approach here algebraically. So we want f of r plus h minus f of r, and I'm just going to bring this down and subtract the original function. And I'm leaving it this way. I'm leaving the 4/3 out because now I'm going to look at this as like I've got a common factor of 4/3 pi among these sort of two things that I'm subtracting. And I'm going to take out that factor of 4/3 pi. So inside I've got r cubed plus 3r squared h plus 3r h squared plus h cubed minus r cubed. Now we see that the r cubes cancel, and everything that's left has an h in it. So in my next line, I'm just going to go ahead and factor out the h. So what's left inside is what? 3r squared plus 3rh plus h squared. So there's f of r plus h minus f of r. We do all this work to figure out what goes in the numerator of that limit that we're setting up. So again, you know, we want dv/dr. This is the limit as h approaches 0. F of r plus h minus f of r all over h. This is the limit as h approaches 0. H times, 4/3 pi h times 3r squared plus 3rh plus h squared all over h. And now we cancel. At this point, you know, I think probably we've done this limit so many times that when we just see it show up in a polynomial, which is just these last two problems have been polynomials, it's kind of like almost tedious at this point. I mean, if algebra itself weren't so enjoyable, we could call this tedious. But we know exactly how it's going to go, right? We know that that when we expand things out, that everything without an h is going to cancel. Then we can factor out an h. We're going to cancel the h's on the top and the bottom. And now we want the limit as h approaches 0 of 4/3 pi times 3r squared plus 3rh plus h squared. So if we let h, you know, now we can let h go to 0. There's no h's in the bottom. We'll let h go to 0. That makes this term 0 out and this term 0 out. We end up with 4/3 pi times 3r squared, and that gives us 4 pi r squared. There's our dv/dr. Whoops, sorry. They wanted us to evaluate this when the radius is 2 meters. So let's do that. So we get what, 16 pi, and we can approximate that. What are the units though? Say that again.
Meters cubed.
Okay, so meters cubed is the units for volume. What are the units for radius? Say that again. Meters. So our units are actually meters cubed per meter. Now you might look at that and say, why don't I just call that meters squared? And you could, hold on, I'm just approximating this, 50.27. I suppose you could call that meters squared, but I feel like that you lose information when you do that. This is a rate of change of how does the volume change, you know, compared to a change in radius. The units that accompany it should be a rate. It should kind of imply that we're kind of comparing two quantities. Meters cubed per meter gives you that comparison, whereas in meters squared, I feel like you lose something. However, you might think, wow, that's weird that the meters cubed per meter, you know, like that just reduces to meters squared, which of course is a unit of area. So I just want to take a moment right now and appreciate this. If you look up on the internet or in a book, or maybe you happen to memorize this, but the surface area of a sphere of radius r is 4 pi r squared. Like, if you take the derivative of the volume of a sphere, you get the formula for the surface area of a sphere. It's almost as if the sphere knows its own rate of change with respect to radius. And that also kind of gives some interesting insight into how we get meters, having meters cubed per meter kind of reduced to meters squared. That's an interesting point of conversation. So the next time, you're at a party or something and it's dying down, just mention this. You'll get people talking. Talking about what? I don't know, but they'll talk about something. You want to do another one? Yeah, just get into it. Just be like, yeah, like if you have like are excited, fake it till you make it, I guess. Just get excited about it. It's a lot more fun when we start a new problem. Okay, so let's read through this. The power P produced by an electric current I in a resistor varies directly as the square of the current. And then, given that 1.2 watts of power are produced by a current of 0.5 amps in a certain resistor, find the expression for the instantaneous rate of change of power with respect to current. Okay, I'm going to stop there for a second, and I want everybody to understand that, I have no background in circuits, in electrical engineering at all. I can read this, though, and understand what they want me to do, looking at the language that they're using. So there's going to be, when you look through the exercises, which are posted to Canvas, because these don't come out of the Larson text, they come out of a different book. But when you look at the problems, there's going to be a lot of kind of specific application problems. You don't need to understand necessarily those particular applications in order to know how to read and parse out the information they're giving you and what it is they want you to find. So I'm going to start with just identifying our goal. Find an expression for the instantaneous rate of change of power with respect to current. So power is P and current is little I. That means that they want us to find dP di. That's important to identify the goal, because what that means is that now I need a function, I need an equation that gives me P as a function of I. I want only P's and I's in this equation. So now let's go to the top. They tell us that the power P produced by an electric current I in a resistor varies directly as the square of the current. Varies directly as means the same thing as is proportional to. That tells us how we start this, getting this equation. If something is proportional to another quantity, if one quantity is proportional to another one or varies directly as another one, it means that that quantity is just some constant, usually we call it K, times the other quantity. And in this case, the other quantity is the square of the current, so that's I squared. In electrical engineering, little I always represents a variable current. If you look at engineering textbooks, instead, you might have done some work with complex numbers, but this little I is not the square root of -1. If you look at engineering textbooks, when they work with complex numbers, and they do, they'll use J as the square root of -1 for this purpose. But this is all by way of me saying that I squared is not equal to -1 here. It's a variable. So they tell us that it varies directly as the square of the current. That gets us a start, right? We don't quite have it down yet because there's this unknown constant K. We call it the constant of proportionality. Now they tell us 1.2 watts of power are produced by a current of 0.5 amps. They've given us a matched pair of values of a power and current. So we're going to use that information to figure out what K is. So 1.2 is equal to k times 0.5 squared. If you square 0.5, you get 0.25. And now we can solve for k. Dividing by a quarter is the same as multiplying by 4, so this gives us 4.8 equals k. Now I know what my function is. So we did have to do a bunch of work just to figure out what the function is. If I know that k is 4.8, the next thing we're going to do is just, plug this in for k in that initial equation that we were able to set up. So our function p is equal to 4.8 I squared. That's like our f of I. I'm going to stop there for a minute and just see if there are questions on how we kind of interpreted the given information or, proceeded to use it and set up our equation. Okay. All right, so now we're going to find the derivative. So now we get to set up our limit. So dp di is the limit as h approaches 0, f of I plus h minus f of I all over h. I'm just going to go ahead and throw in, do the algebra all up in the fraction because it's kind of a simple function. I think it's easy enough to do it up within the limit. So 4.8 I squared. There's our f of I plus h. 4.8 times I plus h squared, rather. And then minus 4.8 I squared. That's minus f of I all over h. We're going to FOIL out that I plus h squared. And we could either distribute that 4.8 or I'm going to take the approach we did last time and just say, look, I've got this common factor of 4.8, so I'm going to take it out. And when we do that, we've got I squared plus 2IH plus H squared minus I squared. Yeah. Yes, okay, good. Thought I missed a term. I think I got them all. And we know what's going to happen. Again, this is polynomials, right? So we know, look, the I squared minus I squared. That's no surprise. Everything that's left inside has an H in it, so let's factor that out, and then we can cancel. So when we factor out the H, we get 2I plus H. We're going to cancel the H's. 4.8 times 2I plus H. Now we can let H go to 0. It's pretty old hat by this time, I think. 4.8 times 2 is 9.6. So 9.6i is dp di. There's the derivative of power, or the instantaneous rate of change of power with respect to current, like as a function, right? So now if I want to figure out what the rate of change is for a particular value of I need only plug in the value they gave me, which was 2.5 amps. And that gives us 24. So, what are the units here?
What?
Say that again.
Watts over
Amps, yeah. Right, because, we're just taking our Q. This is the great thing about the using dPdI instead of P prime, right? This gives us a reminder. I'm just going to take the units of power over the units of current. And those are the units of dPdI. Okay. Questions? Okay. So let's now, in this next section, we're going to learn some rules. In the next several section, we're going to learn a bunch of rules, okay? Like, how do we take the derivative of something that looks like this? Or how do we take the derivative of something that looks like this? It's going to feel like a lot of rules that we're learning, and I guess in one sense it is. But every time we learn a new rule, it's something that it's going to allow us not to have to set up the limit as h approaches 0 every single time. We take a whole page sometimes, half a page, a whole page to find a derivative of a function. And the rules that we're learning are going to allow us to do it in like a line or maybe a few lines if it's a complicated function. So we're going to start by focusing on polynomials. And the first rule is just the derivative of a constant. So the derivative of a constant is always going to be 0. When you think about it, a derivative is a rate of change. So if your function is constant, its rate of change is 0. It's not changing at all. Another way to think of that is if you have a function like y equals 5 or something, it's just a horizontal line. And the slope of a horizontal line is 0. So that first rule should make sense, I hope, that the derivative of a constant is 0. As you've been working on the exercises, you may have already noticed this pattern for like what the derivative of x raised to a power ends up being. And as it turns out, we have a nice rule for this. The derivative of x to the n power, you just take that power that x is being raised to, and you bring it down in front, and then you reduce the power by 1. So when we were using the limit to find the derivative of, x cubed, you did the whole stuff with the limit, and let's FOIL this out, and it just ended up being 3x squared. So that's a pattern that holds. Anytime we're just raising x to a power, we can bring the power down in front as a factor, and then reduce the power by 1. The constant multiple rule. So in these rules, by the way, c is always a constant. U and v are always functions. In calculus, a lot of times we use f and g, and also a lot of times you see u and v used a lot. So the constant multiple rule says if I'm multiplying some function u by a constant, I can just pull it out. And that'll be a pretty handy rule. It's really important that's only true for a constant, not variables. I can't pull out a factor of x. And then the sum and difference rule says that we can split up a derivative over addition and subtraction. So if I'm adding a couple of things or subtracting them, I could just take the derivative individually and then add or subtract, depending on how it looked in the original expression. What's really important to note here is that there's no rule on this page that tells us what we do if we're multiplying two functions. There's no u times v or u divided by v. We're going to get to that later. So we'll do a little practice, and then we'll take a little time, I think, to derive the power rule to kind of get us all to believe that it's true. But let's use these rules. The first one, if my function is y equals 5, what is dy dx?
Yeah.
Say that again.
Yeah.
0. Yeah, it's a constant. Derivative of a constant is always 0. If y is equal to x cubed, what is dy dx?
3x squared.
3x squared. We bring the power down and reduce the power by 1. We didn't have to set up a limit. It's so nice to just look at it and say, here's the answer, right? And this is not poor communication or anything. Like, there doesn't have to be a ton of work to do for these. Don't worry, we're going to make things more complicated, but learning these rules is what's going to allow us to do more complicated, work with more complicated functions, all the while without having to set up that limit. Our next example, just y equals x. If we're finding the derivative, I think it's important to remember that x is the same as x to the first. So, what if we use the power rule? Like, it's okay if we don't have like the final answer, but like, what does it start to look like if we use the power rule on this? Say that again.
1x.
To the 0 power, yep. What is x to the 0?
1.
1. Yeah, anything to the 0 power is 1. So in fact, dy dx is equal to 1. Now this is going to, some books present this as a whole separate rule, and I don't do that because it's really just a special instance of the power rule. But the derivative with respect to x of some constant k times x is just k. So like the derivative of 5x is 5. The derivative of negative 3x is negative 3. And that, I hope, will make sense when we think about how the derivative, one interpretation of a derivative of a function is the slope of a tangent line. Well, a constant times x is just a line. It's a line of slope, whatever that constant, coefficient on x is. So I hope it makes sense that the derivative of k times x is equal to k. This is a line of slope k, right? So its derivative should just be k at every point. Questions so far? Okay. All right, let's do some more. The derivative of 3x squared. So we're going to have to combine a couple of rules. One is the constant multiple rule. The constant multiple rule is the one that says we can pull the constant out. But the way that we kind of use that in practice is just bring that 3 down with us. And now multiply it by whatever the derivative of x squared is. What is the derivative of x squared?
2x.
Yeah, 2x, right? 2x to the first, or just 2x? And then I'll simplify 6x. As you do more of these, you're going to get real fast at just looking at that and be like, oh, that's 6x. I bring the 2 down and multiply it by the 3 that's already there. I get 6x. There's my derivative. We're going to combine 3 rules now. First, just note that we are adding and subtracting some terms. So we're going to get to approach this term by term, right? And each one of these, I'm going to need to pull a constant factor down with us. The first one, I'm bringing down the 5. What's the derivative of x to the 6th?
6.
6x to the 5th. Now I'm bringing down the minus sign. And I'm just approaching the next term. So I have a factor of 2. The derivative of x to the 5th is 5x to the 4th. Bring down this plus. How do we find the derivative of 4x squared? Great. Bring down the minus. And the derivative of 3? 0. Now I'm going to simplify. So I'm just going to multiply, right, these coefficients. So I've got 30x to the 5th minus 10x to the 4th plus 8x, and then, you know, I'm going to leave off the 0. So we can sort of see how in a couple of steps, you know, that we're combining multiple rules to get the result. But again, you know, if you do a few of these and before long you're going straight from this right to the answer. Like, and that's the point. Finding the derivative of a polynomial can be easy. We don't have to make it harder. Just, you know, be careful with your signs and your, you know, like little mistakes, you know, careless mistakes can still happen. But it's, if you went straight from the beginning and just wrote down a one-line answer for this, that's fine, right? Like, that's not poor communication. Like, it really can be that simple, when, especially when we're working with polynomials. Questions before we do one more? Okay. All right, so the last one in this section says find f prime of 1 if f of x is 4x to the 7th minus x cubed. So we're going to just find f prime of x first. Let's get the derivative, and then we'll evaluate it at 1. That's all we're doing here. What should we get for f prime of x?
$28x minus 3x squared.
Nice. Good. Right, so we just brought, you know, we just used the power rule, and if we needed to, like we did in the first term, multiply, when we bring that power down, multiply by whatever coefficient's already there. F prime of 1. It's pretty simple. 28 minus 3 is 25. We just found like 8 derivatives in, you know, in 2 pages that would have taken us easily 5-6 pages before if we had to use the limit definition. And also, I just want to appreciate right now, like, finding the derivative of a polynomial using the limit definition got pretty, you know, rote. Like, right, like it got, like there's a rhythm to it. We kind of know how it's going to work. So it's not that it's like the most challenging thing like that we did, you know, in the last section. But I just, you know, think about how much space and time would be required to find the derivative of this function, 4x to the 7th. So this would be, you know, going down to the 7th row in Pascal's triangle to set up that limit and evaluate it and do all the algebra and simplifying when we really have these nice sort of shortcut techniques. I want to just let you know that on the quiz that you're going to take Friday, there will be one problem that says use the limit definition to find the derivative. And that means I want you to set up the limit as h approaches 0. On any problem, and that goes for the quiz, that goes for when we take the test on this chapter later, unless a problem says use the limit definition, just use these rules. Use the rules that we're learning. You don't have to, if you love the limit definition, you can use it. It is the definition of the limit, so it can always get you there, but unless you're specifically asked to use a limit definition, you don't have to do that. What I want to do now is take a little time and derive the power rule. So this is not in the notes packet itself. This is sort of for your entertainment and edification. So I'll start with this. We know that we're going to have to find x plus h to the nth power, right? What makes that difficult and challenging is that n is not a fixed number, right? Like, it's hard to think about expanding something when we don't have like a fixed value for that exponent. But we're gonna learn some patterns. We're gonna know enough to be able to figure out what this limit is. So I'm gonna start just with Pascal's triangle, right? This is one that begins 1, 1, 1, 1, 2, 1, and then each row begins with a 1, and then you add. Right, so our next row is 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, and so on. So if I'm looking at x plus h to the n power, I want to go down to the row that begins 1, n. And then there's a bunch of other stuff here, but I know that it's symmetric, so that it ends n1. And as it turns out, the fact that we don't know what all those other values are going to be doesn't matter. Like, we're going to be just fine. So we'll just sort of keep this in mind. This is the row that we're going to need. So the derivative of x to the n is the limit as h approaches 0 of x plus h to the n minus x to the n all over h. X plus h to the n. So I know that it starts out with all x's, right? X to the n plus my next coefficient is just n, and then my power on x goes down, x to the n minus 1. I introduce a factor of h plus, I don't know, some coefficient, x to the n minus 2, h squared, and so on and so forth, plus nx h to the n minus 1 plus h to the n, and then minus x to the n. So if we're looking at what we have up top, we start out with a x to the n, and then at the end we're subtracting x to the n. Those cancel. On top now we have n x to the n minus 1 times h plus something x to the n minus 2 times h squared plus, now all those terms that I just kind of, have the dot, 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 right? There's a bunch more terms. They all have more factors of h, right? Like the factors, the power on h kind of steps up each time, right? So we start with no h's, then we have a factor of h, then we have h squared, then we'll have an h cubed and an h to the 4th, up until we get toward the end, nx to the, times h to the n minus 1 plus h to the n. So what I want us to see is that every term has a factor of h. The first term here just has a single factor of h, and all the other ones have more h's. So they all have a factor of h. Let's take it out. So if I take out that factor of h, then the first term is n times x to the n minus 1, plus we have some unknown coefficient times x to the n minus 2 times just h to the first now, because I took out a factor of h, plus a bunch of other terms that have more h's. They all still have a factor of h, at least one, more than one, in fact. Then we have n x times h to the n minus 2 plus h to the n minus 1. So we took out this factor of h because of course we want to cancel it. But look at what's left. Every term, all the terms in here, these last two on the end, they all have a factor of h. So when we let h go to 0, they all zero out. And the only thing we're left with is n times x to the n minus 1. Fun? Yeah. That's what I thought. Okay. All right, so we have about 20 minutes left, I think, right? So let's go ahead and get a start on this next section. We probably won't finish it, and that's okay. But we're going to look at how we take the derivatives. This whole next section is about how do we take the derivatives of products and quotients. You know, I'm going to go back to the section we just finished and look at that list of rules that we had. This last rule said we could split up a derivative over addition and subtraction, right? Just find the different derivatives and like add and subtract the terms. And I said at the time, you know, that there's no rule on this page that tells us how we take the derivative if we're multiplying functions or dividing functions. We have special rules for those. So we start with the product rule. So if I have two functions, f and g, the product, f times g, has a derivative given by this formula, g times f prime plus f times g prime. Essentially, you could think of it as we're taking turns of which function I'm taking the derivative of, right? We're adding a couple of products, right? Like g, f, f, g, and we're just taking turns which one we're taking the derivative of when we multiply them together. When the first step in using the product rule is knowing that we need to use the product rule, recognizing that we need to use the product rule. If you're multiplying two things and they both have x's, you know, they both have variables, you have to use the product rule. We can't just split up a derivative over a product. You could try it. You'll see like it gives you a different result, which is not equal to the derivative of the function you're looking for. In the beginning with these functions, they're all functions like these two that we're going to do here and some in the homework are ones that we could find the derivative of other ways. Like, for example, if we're looking at this product, we could find the derivative just by foiling it first, and then we have a polynomial, right? And then we're back to the last section. I'm introducing this, and we're going through these examples first on these functions that we have other techniques where you'll see you can convince yourself that this formula is valid. You'll get the same result that we should get when we if we were to multiply things out first. So I'm multiplying two things. They both have x's, so this is a product rule problem. We just have to identify f and g, and with the product rule, it doesn't make a difference which one you pick for f and which one you pick for g. As I'm a creature of habit, so I always let the first function be f. So here, I'll say that f is equal to x squared plus 3. And then that means f prime. What's f prime? Two x. Our g function then is 3 minus 2x. What's g prime?
Negative.
Okay, so h prime of x, which is the derivative we want. I'm going to start by writing the product rule. The product rule is something you need to know. It won't be provided for you, so I'm going to just write it out every time I need to use it. G times F prime plus F times G prime. So that is 3 minus 2x. Now I'm just substituting in, right? I'm just substituting in. There's G times F prime we found is times 2x plus F, which is x squared plus 3, times G prime, which is negative 2. So there, I've put this together. What I have written down is equal to the derivative, h prime. Of course, we're not done yet because we need to simplify. This is like horribly unsimplified. Definitely don't want to leave it in this way. So I'm going to distribute, I'm going to expand out each of the products, and then combine like terms. So let's see, if I distribute the 2x, we get 6x minus 4x squared. And now I'm going to distribute this minus 2, so we have a minus 2x squared minus 6. And combining like terms gives us negative 6x squared plus 6x minus 6. You could leave it there, or you could factor out the 6 if you like. I don't think it will unfoil. I'll factor out the negative 6, so we get x squared minus x plus 1. Either of those is fine. You want to do another one?
Sure.
Yeah. Okay, what's the first step when using the product rule? What's that?
Recognizing you need to use the product.
Yeah, we have to recognize that we have to use the product rule. Could somebody explain to me why this is something that requires us to use the product rule?
Two functions that are complex.
Yeah, there's x's in both of those, right? It's not just a constant times some function, but there are two functions of x. So we are going to identify our f and g. I always let f be the first function, but you could mix it up if you like. So f is 3 minus x minus 2x squared. And then what is f prime?
Negative 4x minus 1.
Say that again.
Negative 4x minus 1.
Not negative. No. So the 3 is a constant, right?
That's 0.
So that's 0. Yep.
That's minus. That'd be 1.
Minus 1. Yep. Oh, did you say negative 4x minus 1?
Yeah.
Oh, I was trying to read it in the other order. Okay. Yep. That's perfect. Thank you. Don't mind me. It's just a Monday morning. All right. G is x to the 4th minus 4. What's G prime?
4x cubed.
Great. Okay. Let's put this together. dy dx is equal to, I'm going to start out by writing the formula. G f prime plus f g prime. And now I'm just going to plug stuff in, right? I've already done the work to set this up. Now I'm just going to plug stuff in and get myself set up to do the algebra that I need to do to simplify. G times f prime, that is x to the 4th minus 4 times negative 4x minus 1. plus f 3 minus x minus 2x squared times g prime times 4x cubed. What we have here is in fact equal to dy dx. It's just not simplified, so we don't want to leave it in this form. Let's expand these products, combine like terms. If we FOIL out in the beginning, we get negative 4x to the fifth minus x to the fourth plus 16x plus 4. And then distributing the 4x cubed, we get 12x cubed minus 4x to the fourth minus 8x to the fifth. And now all that's left to do is to combine like terms. So here's our x to the fifth terms. That gives us a minus 12x to the fifth. Our x to the fourth terms. That's negative 5x to the fourth. And then there's no other like terms, so plus 12x cubed plus 16x plus 4. Questions on that example? Okay. On the next page, it introduces the quotient rule. What I'm going to do is hold off on the quotient rule for now. I'm going to take a few minutes, and we're going to just derive the product rule together. We're going to sort of see why that the product rule looks like this. I mean, this formula seems maybe a little bit contrived, and actually kind of convenient. It's kind of nice how it works out this way. But I'm gonna let's take a little while and just sort of show why the product rule looks the way it does. You could take notes on this. You could just enjoy, take it as entertainment. I'm not going to ask you to derive the product rule for me, but I'd like to kind of show as much as I can a rationale behind all the rules. Get it to the point where we believe it. So if we want the derivative of f of x times g of x, right? This is what the product rule allows us to do. We know how to find the derivative. We know the definition, right? The limit definition. So this is the limit as h approaches 0. And then what that is like f of x plus h minus f of x all over h. So here, if our function is f of x g of x, then that x plus h part is f of x plus h times g of x plus h minus f of x g of x. All over h. Now deriving, I'm going to actually need some space here, so I'm going to move back. Deriving the product rule involves us employing one of the oldest tricks in mathematics, and that is we're going to add 0 to this expression. We're going to add 0 to the numerator, but we're going to do it in a clever way. So the numerator I'm going to write as my first term, f of x plus h, g of x plus h. Then I'm going to subtract and add the same thing. I'm going to subtract f of x plus h times g of x. We're allowed to add and subtract the same thing, right? It's just adding 0 and then minus f of x g of x. Now I'm going to split up this fraction over the addition that's happening right here. All right, so I'm going to have this stuff over h and this stuff over h. Now for the first fraction, there's a common factor of f of x plus h, so I'm going to write that out in front. And then up here I've got g of x plus h minus g of x plus, in the second fraction, I've got a common factor of g of x, so I'm going to take that out. So I've got the limit as h approaches 0 of this sum, of the sum of these two fractions, right? When you're finding, you know how we could split up a derivative over addition and subtraction? That's because we could split up a limit over addition and subtraction. So, you know, I'm thinking of this right now as the limit of all this stuff. But I'm going to split it up and write it as two different limits, so that this is really the limit as h approaches 0 of f of x plus h times g of x plus h minus g of x all over h, plus the limit as h approaches 0 of g of x times f of x plus h minus f of x all over h. We can also split up limits over a product, not derivatives, but the limits over a product. So this is the same as the limit as h approaches 0 of f of x plus h times the limit as h approaches 0 of g of x plus h minus g of x all over h, plus the limit as as h approaches 0 of g of x times the limit as h approaches 0 of f of x plus h minus f of x all over h. We're almost done. Like here, that first limit, right? The limit as h approaches 0 of f of x plus h. If h goes to 0, that's just f of x. This, I hope we recognize, that's the derivative of g of x, right? That's the limit definition for the derivative of g of x. So that's g prime of x. Over here, as h approaches 0, well, g of x is g of x. There's not even an h in that expression, so that just stays put where it is at g of x. And this part here is the limit definition of f prime of x. That's the derivative of f. Thus, the derivative of f times g is equal to that expression there. Questions? Okay. Well, if that's if there are no questions, I think that's as far as we'll get today. There are practice exercises here listed for the products of quotients. Obviously, we didn't finish that section, so If you know, it's fine to wait until we finish covering that on Wednesday to get started on those. But there's this handout or the PDF posted to Canvas that's got practice exercises for that instantaneous rate of change, like those word problems, and then the derivatives of polynomials, like learning some of those shortcut rules, is back into the Larson text. Don't forget to get your assigned problem. They're posted to Canvas. If you have questions, it's okay to ask questions on those problems. It's okay to work together. If you're assigned the same problem, you can refer to your notes. The only requirement is that you turn in a solution that accurately reflects your understanding of the problem and the solution that you're turning in. I will see you all again on Wednesday.